Good morning to everyone. Myself, Ramandeep, Behl, working as an associate professor in King Abdulaziz University, Saudi Arabia. This is our joint work with Professor Chang Bung Chun from South Korea and Dr. Sonia Bala from India. So the title of the talk is Two-Step Iterative Method for Multiple Roots and Their Application for Solving Several Physical and Chemical Problems. So this is the index of our presentation. First of all, we give some introduction about our research, then development of a new scheme and their convergence analysis. Then later on we will discuss some selective cases of our schemes, then numerical results, and there is another way for comparison of iterative methods based on the basin of attraction, where we check generally the stability and other stuff. Then later on, finally, the conclusion and references. Here, there are so many problems in different area of science, engineering, chemistry, and other applied sciences that having a root with multiplicity m, such as CSTR, continuous stirred tank reactor problem, van der Waal equation problem, etc. so on. Mathematically, a non-linear equation is said to have exact root x star of multiplicity m if it satisfies these conditions. Sometimes it is hard to find the roots of such equation with the analytic methods. So that's why there is only option left for us. We have to focus on iterative methods. Okay. No doubt there is plenty of iterative methods available in the literature, okay, but all iterative methods are not working for each and every problem. So that's the only reason we have every time new refined iterative methods. Okay, so here in this paper we focused on a fourth order schemes based on weight function approach. Okay, the advantage of our schemes we will discuss in the next slides. Our scheme also fulfill the Kung-Trop conjecture. According to that, our scheme is a optimal. So here is our new schemes in 2.1. So here you can see that generally whenever we authors or searcher construct a new iterative method, generally they are taking here Newton methods, okay, or some other second order iterative method. But here we are giving them flexibility p of mu, mean you can choose any function, whether it is a Newton method or any other second order iterative methods, but it satisfies some condition which are defined in the next theorem. And here again in the second step we applied a double Newton with another weight function g mu, where mu and nu are defined here. Okay, so here nu is a multi-valued function, so obviously we have to focus on analytic function. That's the reason we define in the beginning p of mu and g of mu are two analytic functions in the vicinity of the origin 0. Okay, so let's discuss next theorem on that. So we are saying that suppose h as a function, h be a holomorphic function in the region D, let x star be a multiple 0 of that with a known multiplicity m greater than equal to 1. Then our proposed scheme has fourth order of convergence if these conditions are satisfied. These conditions. Sorry. The scheme 2 convince the following error equation. So this is our error equation. If any you can choose any weight function provided it should satisfy the condition of 2.2. So let's have a look on the next slides where we discuss some new cases as well as the old cases. Okay, if we choose a p of mu as only simple mu and and weight function g of mu as this one. Then we can easily get the existing method ZH1. Okay, similarly, same P of view and then this kind of weight function, then we will get a new scheme, or sorry, existing scheme of ZH2, Zhao schemes, that is. Okay, so here we discuss some new iterative method where we choose P of mu as a rational function. Okay, here you can see that some new functions here as well as this function. So the combination of this one, we given a name for comparison m1, m2, m3, m4. Even you can choose exponential functions. Any function which satisfies the condition of 2.2 you can use for new methods here. Okay, so these are a, b, c, r all are real numbers, and for the comparison point of view we assign some values. These are the values here. So numerical results. We also compare the numerical results with the existing method Zhao et al., which I shown you in the previous slide, ZH1 and ZH2 here. Okay, so some other methods, Soleimani and Babaji and Jafar et al., you can see it here. These are the 6 methods which we are going to compare these our iterative schemes with these 6 methods. Okay, so these are the software which we used, Mathematica 11, and E epsilon is the difference between two consecutive iteration, and this is known as absolute residual error. This is the formula we used for ACO, approximate computational order of a convergence. So these are some notations which are we used in the table. So here we choose first one problem, eigenvalue problems. Whenever we have any matrix whose order is greater than 4, it is hard for us to find the eigenvalue of that. So here we can use our iterative methods to find the eigenvalues. So for this purpose we choose a 9 by 9 matrix which is given here. This is the characteristic equation of that one, and let us say x star 3 is the eigenvalue or root of this equation with the multiplicity m is equal to 2, and we choose initial approximation x naught is equal to 2. Results are given in the following tables. So you can see it here, Zhao H1, Zhao 2, Soleimani, and some other methods. Okay, Zafar Ali et al. All these 6 methods, you can see that here the difference between the error, 2 consecutive iteration, the highest among, sorry, the lowest among them it is this one, 7.875, but at comparatively this one. So you can see there about almost 9 significant digit differences. Similarly, here the residual error among them, this is the lowest residual error, but you look at here, almost 150 significant digits differences. Okay, and our method is also more stable, like 4th order other methods. Next, we again choose another problem of potential problems, Leonard and Jones potential problem, which is given here 4.1. So once we use the values of some parameter, we can get this equations. So here minimum value is this one, and we choose m is equal to 1, multiplicity 1. We want to show it that our method also work for simple root as well. So here is the numerical results. Again you can see that S1 and Z1 are diverged from the root, and here the computation order of a convergence. Again the residual error -0.38, and here lowest is 0.26, which is again shows these method, the existing method, have a higher residual error as comparative to our one. Okay, so another way of comparison sorry, the basin of attraction is a significant tool that depicts the stability behavior of a method on the complex plane. Okay, so here we choose near about 7 problems, P1, P2, P3. These are their roots as well as the multiplicity. Okay, so here what are the criteria we choose for here? All the functions have a root within the square -3 to 3 by 3 by 3, and we took 250,000 equally spaced point in the square, this square, each point is assigned as a different color. Okay, the point black color mean the method did not converge after 40 iterations. So here are the basins of attraction of the root polynomial based on this one. So this first picture, the first row is the method, existing method ZH1, ZH2 and S1. Similarly, existing method this one Z1, Z1, Z2, Z3. So these are our method M1 and M1 as well as M2. So you can see from the picture there are more black points as comparative to our methods. So we can say that these methods have more divergent point as comparative to our methods. I'm so sorry. Next we have another polynomial equation, this one. So again you can see it here. So this is existing methods, again these are existing methods. So again we have less number of divergent point, brighter basin of attractions, and wider range also as comparative to them. So we can say that our methods are superior than the existing methods. So we also checked the performance based on the average number of iteration, all the polynomial P1, P2, P7s. Okay, so here are the polynomials. These are iterative method, existing methods. So you can see that our average is quite below as comparative to them here. Then we again also check the CPU timing. So you can see the CPU timing is also lower, but not lower than S1 and Z2, because in some cases these methods are not divergent. So that's the reason. Okay, here. So you can see it here. So here is the number of points requiring more than 40 iterations for each functions here. You can see the percentage which is out also good, quite good. So the concluding marks. So in our scheme we given the flexibility to the scholars that they can develop as many as new methods by just changing two weight functions in the first step as well as in the second step. In the earlier study only either in the first step or in the second step. Okay, the proposed method are not only work for m greater than equal to 2 but also work for simple root. Next, our scheme also optimal in the sense of Coombe and Trop conjecture. The reason we are using 3 functional evaluation. So at each step, so according to Coombe Trop conjecture, the maximum optimality is what? 2 power 3 minus 1, that is 4, and we are attaining the 4th order convergence. So that's why we can say that our method is optimal. Next, we also present several physical and chemical examples which are for more details you can see our paper. So here we just only given 2 examples and we found that results are quite effective, comparable and supports the theoretical result. At last, the basin of attraction of our scheme also confirms the same result for the performance of suggested techniques as compared to the existing one. So these are the references. Thank you very much for your attention. Any question, any query, please let me know. Thank you very much.